Thank you. Thank you for that wonderful introduction. So, like she just said, I have this book, and uh, one of the interesting things is that when I started as a professor some time ago, like 6 years ago, I thought I'll start a course called Flexible Electronics, like a full semester course, and I was looking for reference textbooks. At that time, I couldn't find any. So I thought I'll write one. So it's always I mean, for young researchers, I would like to point out if there are no textbooks available in your field, it's not really a bad thing. It's actually an opportunity for you guys to write one, right? So that's always there. And if you're interested, please scan this QR code and buy the textbook so that I get royalty from it. Um, Apart from that, I also like I said, apart from that, from the flexible electronics, I also work on applications of sensor systems. I mean, we make sensors using flexible electronics, but what do we do with them? So we typically work with, for example, IoT applications, smart cities, healthcare, medtech devices, and so on. That's where we typically try to apply these whatever learnings we have from flexible electronics. So that is what we will be talking about today. It's an entire. I mean, I want to close the loop for one particular sensing technology that we have been trying to use. That's piezoresistive sensing, and we want to. I want to go through the motivation for it and why we chose that particular thin film technology and how it works. So first, the why part, the motivation part, like why we want to use sensing, and I typically start these kinds of talks with a game. I'm sure when you were young, you must have played this like a cartoon. Pictures are there, and you have to spot the difference between the two pictures. I mean, we used to play that when we were little, and I always ask my students to spot the difference between these two pictures, right? So, I mean, you don't have to answer. It's a rhetorical question right now, but the point is they actually they're looking more and more similar as time goes on, right? I mean, robots didn't used to look like this just 10 years ago, for example, or 20 years ago. And 20 years from now, how they'll look like, whether they'll start looking like exactly like this or not, is the question that we are here to answer, right? And we as researchers, it depends on us as researchers of flexible electronics to answer that question, whether those differences are going to go down. And even if they look similar here, you will realize that internal structures are not really that similar. I mean, they're actually very different from each other in terms of uh, literally every aspect of engineering. I mean, for example, the way actuation works in robots and human-made robots is very different from the way actuation works in what I'm going to call nature-made robots, right? The way processing of information works in the brain is very different from the way it works in robots, and sensing and everything else is very different. So a lot of engineering gaps are there, and you can argue that nature-made robots are superior to a lot of uh, things that human-made robots can do. So we want to reach there. I mean, at least in some aspects of engineering, we want to reach there. And what are the things we want? We need to have is a flexible, stretchable, thin film, low cost sensor system, right? Sensor meaning in this case, for the five senses that we have: eyes, olfactory, skin, etc. Um, we want it to be flexible, we want it to be stretchable, we want it to be thin film based, because these muscle structures are like that. Low cost, obviously, so that we can apply them everywhere and democratize them. These are all need to have. You have to have these. Nice to have would be, can we make them grow, heal, and regenerate? I always tell my students this. I mean, when I say this, they always laugh. But wouldn't it be nice if your iPhone grows, right? If you feed something to your iPhone and it grows, it's not physically impossible. I mean, my kid grows, right? So why can't an iPhone grow, right? They're both made out of the same elements that are there in the periodic table. The physics and chemistry of systems is the same in this universe. So if humans can grow, I think cars should be able to grow, right? So we are basically doing something wrong. at least they should be able to heal, if nothing else, which people are actually working on. And reproduce, I don't know. That's wild, but if your iPhones can reproduce, it will be interesting. But all of these things are kind of nice to have in a structure, at least, if not in a system. So we'll basically go through these, and the sensor part is important because if you look at the way information is being processed right now, right? We talk about cloud computing. We talk about processing information even on the edge. I mean, when robots, etc., process it, they typically do it through a digital medium. I mean, right? Zeros and ones are being processed, right? And I always sort of point out this variation between the real world where we live, and breathe and everything else, and the digital world, right? There is a divide between the two these days. I mean, there's an entire world where all of your information is living, right? All of who you are, all of Wikipedia, all of Google, all of internet, all of Facebook, everything is there in this digital world, what I call the matrix. And there is this real world. And the interesting thing is, we go back and forth from the real world and digital world without even knowing about it. I mean, a classic example that I always give is, for example, when I'm speaking something, right? It's you guys are able to hear it because it's going through the digital world and then back into a speaker, right? It's going from the microphone to a amplifier to a processor to a speaker, and then you're able to again hear it in the real world. So this divide between the real and the digital world is not that heavy, and the things that bridge it are basically your sensors and actuators, right? That's what is bridging this divide. I mean, so you're going from, for example, anything in the real world needs to go through a sensor to the digital world, right? There's no way of getting around it. I mean, there's no other way of doing it. And from the information world, if you want to control or influence the real world in any way, for example, speakers are controlling the sound or pressure waves in the air, lights are controlling the photons in the air. So all of those things are actual influence that is happening on the real world that needs to be done using an actuator, right? So this is how we close the loop. And in the matrix itself, we do processing, analysis, storage, transmission, everything, AI, everything is sitting basically in that matrix, right? So because we are tied to the real world, and because the matrix has become very important at least in 2025, uh, sensors and actuators that are the bridge between these two are obviously now becoming very important, right? We need to worry about them and their engineering, and figure out how to make them work well. So this is what we are basically here to talk about. Now, coming back to the humanoid problem, I mean, because we are talking about flexible pressure sensors, the classic example of a flexible pressure sensor is a skin, right? You want to basically look at how skin works. I mean, uh, as the final example, or the epitome of achievement for a flexible pressure sensor would be if it can mimic the way the skin works, right? So the best way to realize the best way to do that is to figure out first how the skin works, right? And what kind of sensing it has and how it senses, and figuring out, for example, the thresholds that are associated with it, right? For sensing and force measurement and all. Now, if you look at the skin, it typically has these kinds of sensing systems. There is a pressure sensor that does fixed force sensing. I mean, there are specific discs and corpuscles for different kinds of sensing, but there is a sensor for sensing that is something that is continuous pressure. I mean, if you apply a pressure on your skin and leave it there, you can still feel it, right? That's zero frequency pressure. There's no frequency attached to it. It's just DC pressure, fixed force. You can still sense it using these sensors. And then there are something called texture and vibration sensors. These corpuscles are specifically designed to activate if they perceive a change in a rate of change or a frequency of force applied. I mean, they're not active when you just do a fixed force, but a rate of change of force, right? So at specific frequencies like 20 hertz, 30 hertz, up to 100 hertz is where these corpuscles. So whenever you are basically touching something, and trying to feel something like a texture or something like that, that is when they are getting activated, right? Because when you move your finger across something, that it's roughly at a frequency of 20 or 30 hertz is where you're trying to experience the ridges on that system, and that texture basically is is what you're sensing there, right? So, and of course skin can detect temperature as well. Some people say that skin also is sensitive to light and humidity, but it's a very small signal to noise ratio, so we'll not worry about that. But these are the main ones that we definitely know the skin you know senses very well. So we'll come to that. And in fact, this particular conference in FLEPS 2025, we have a paper in which we are talking about sensing both of them simultaneously, like how we can create a pixel that can sense pressure and temperature simultaneously in flexible form. I'll talk about it towards the end of this talk. Now, having realized that, okay, these are the ways in which skin operates, one of the things that we want to determine is at what thresholds or how sensitive these pixels are. Because if we know the sensitivity of the pixels, we can then map it to our man-made pixels or man-made skin. So this is one of the some of the work that I did back in 2019, or this is the pre-pandemic. In this, what we wanted to do is figure out exactly that threshold, the threshold that I'm talking about, right? So we basically put some actuators that basically just go up and down, like they just actuate like this, and we put like 4 of them and wrapped it around somebody's hand, right? So we basically had this kind of a structure and it's wrapped around like this. So once you do that, now what you can do is you can actuate them, right? And ask someone if they are able to feel it or not, right? And if they're able to feel it, you can then slightly reduce the actuation strength and keep doing that systematically. I'll tell you how the actual system works, but this is what the general idea is, right? Now, the way we wanted to do this is a 3-interval force choice method. What does that mean? It means that in layman's terms, we basically put, I don't know if I have the, yeah. So we basically put a tower light here, right? And we basically have just 3 bulbs in a tower light. So it's actuating 1, 2, and 3. And we ask the user, during which interval did you feel that actuation happen? Was it during the red light, the amber light, or the green light lighting up, right? And it's called force choice because there's nothing called I don't know or I didn't feel it or something like that. You have to choose between the 3, and that choice is recorded, right? So that is what we did. And once we do this, I mean, we ask sequentially the users to basically tell us whether they're able to sense that actuation or not. What we are able to get is the level at which they basically stop sensing it. I mean, they start giving random answers or incorrect answers or so on. So the way you would want to do this is, for example, we started because they're dielectric elastomer actuators. You have to actuate them at a very high voltage. So we started, let's say 1000 volt. It doesn't matter. I mean, if you're using some other kind of piezoelectric actuator, for example, the voltage would be lower, but the protocol would be the same. You would start at an initial force value, right? And if the user answers 3 consecutive times correctly, you will basically reduce it by a certain amount of certain times, like in this case 1.2x, right? So we reduce it to 1.2 by 1.2 times every time the participant's response was 3 consecutive corrects. And if the response is 1 incorrect, we basically bumped it up back to the original level, right? Now, using this method, we were trying to figure out where the sensitivity of the user is. Typically, you will get these kinds of plots when you do this with time. For every iteration, you will, let's say, start at 1000. The user will say 3 correct responses, it will come down. Then again, 3 correct responses, it will come down, and so on. At some point, users start saying incorrect answers. I mean, when the actuation is happening at some other time interval, they will say something else because they're not able to feel it. Now they're just guessing or just a random guess, this thing response. So at that time, you can basically figure out and you can bump it up again, and then bump it up again, and then keep going back and forth. So you kind of settle at a specific value. It's very easy to figure that out. I mean, once you see these graphs, that the users are not able to actually sense above a certain point of actuation. So at that time, that is what you will basically keep as a threshold for a specific subject, right? Now, once you're able to do this over multiple subjects, you will be able to determine the sensitivity of the human skin, like how sensitive it is, and at what force humans are able to sense, and just about sense something. That is very important, because next when we talk about the next part of the discussion, like how to make these sensors, um, that information is very important, like how to control the sensitivity that you're looking for, particularly when you're designing an e-skin solution, right? So now we come to the how part. How do you design that solution? Now, one of the things that we'll talk about today is polymer electronics. I mean, right, organic electronics is a very important aspect to consider when you're designing these kinds of systems. And one of the reasons why is because most of the, like, I talked about these man-made robotics and versus natural systems. um, Natural systems uses electronics that is made of organic materials or material systems, so it does have its upsides. One of the things that you can't do with inorganic substrates or substances is you can't make them flexible, right? I mean, people have been trying, for example, flexible silicon for a very long time, and so on. But the other way of going about it is, instead of taking an electronic system that is already existing and trying to make it flexible, you can take a flexible system and try to make it electronic, right? So that is where polymer electronics comes in. So we are looking at, for example, stretchable materials such as rubbers and plastics, and trying to see whether we can create known electronic structures with them, right? Like transistors and capacitors and memristors and so on. Now, to understand that how to do this, it always it helps to know how organic conduction works, right? I mean, we should always know like the basics of organic conduction. So I just want to walk you guys through how it differs from inorganic conduction. So you're basically looking at these structures are covalently bonded structures, and in them, typically, if you look at, for example, a silicon lattice, the way band structures form in silicon lattice and in inorganic lattices, in organic systems, they form at a molecular level. I mean, so every molecule has its own molecular orbitals and its own DOS, or density of states, corresponding to the nuclear distribution of that particular molecule itself, right? So in silicon lattice, that happens at lattice wide, but in organic systems, it happens per molecule or for a specific molecule, right? So the same principles apply. The first principles, Schrodinger's equation, everything else will apply for the nuclear distribution and three-dimensional potential distribution in a molecule, as opposed to a lattice in silicon. But the band structure it gives is obviously very, very different. So the way conduction happens is very different in polymer electronics. Now, in inorganic, like I said, conductivity arises in these lattice when multiple atoms come together and form these allowed energy states. Like density of states is formed, and a conduction band and valence band gets created, and you can basically get conduction through these free charge carriers. In organic molecules, unfortunately, because this is only molecule wide, it's not from molecule to molecule. So there's no way of electrons to go from one molecule to another, at least no easy way of doing it. It becomes a little more constrained, and it's a very tight conduction that happens. And because of that, the mobility is very, very low in these systems. So these, although they are arising from the same theory, they're actually very different in terms of the structure and in terms of the free electron or free carriers that you can generate out of these, and the amount of current that you can generate out of these. Now, So yeah, for example, a classic example of this is, let's say, any kind of organic structure like a methane structure. You will have all of these, bonded electrons, or these molecular orbitals that will look like this. You will have electronic distribution that will look, again, will basically occupy the lowest energy available for that specific distribution. This is still very similar to the way it works in silicon and germanium or any other inorganic material. But here, the difference is that this is for the molecule itself. Like it's just surrounding that specific molecule is the density of states that we are looking at. So for each molecule, you can actually calculate these density of states instead of calculating it for the lattice. And for example, I mean, you can keep going. For example, there's an ethene molecular orbital structure that will look like this. That will come from two different CH2 orbitals that will look like this. So it'll have slightly lower energy because it's coming together and spontaneously. So that there is a slightly lower energy solution that is available for that particular molecular orbital, but it's still not sufficient to carry electricity across. I mean, across ethene gas or methane gas, for example, there is no way for electrons to jump across these molecules. That is one of the problems that we face in organic conduction. Now, of course, these when you draw out these structures, you can always also have frontier orbitals, just like you have valence band and conduction band in silicon lattice. You can have in molecular orbitals frontier orbitals that are called highest occupied and lowest unoccupied orbitals, or HOMO and LUMO orbitals. So these HOMO and LUMO orbitals are basically kind of equivalent to what a valence and conduction band would be in an inorganic lattice. But again, molecule to molecule conduction is basically a problem in these. And of course, for very small molecules, these differences are between HOMO and LUMO are very large as well. I mean, of the order of 5 or 6 EV, which would of course make it inherently non-conducting to begin with. So then we basically get how do we get organic conduction? Is typically through pi conjugation of these of electrons, and we get that from this structure of single bond, double bond, single bond structure that we get in many molecules in organic systems. And again, at the end of the day, even for these kinds of polymers, you are from the first principle analysis, you're still doing the same calculations, same equations, and you're getting similar molecular orbitals. But in this case, you realize that these molecular orbitals are basically distributed across the molecule in such a way that charge carriers can transport themselves from one end to another, right? So they are basically at least freely able to move across this carbon chain. And once you're able to do that, because of this conjugation, you can actually get at least conduction across one polymer system. I mean, for one polymer chain, right? Now, still there is a problem of hopping from one polymer chain to another. We'll talk about that in a bit, but at least you can get that. And one interesting thing is, in carbon chains in particular, if you have a very large carbon chain, it's shown that with the number of atoms in that carbon chain, you get lower and lower what we call band gap, or between the HOMO and the LUMO systems, something like this. So, for example, if you go from ethene to butadiene to octatetraene or to polyacetylene, you will get the difference between the HOMO and LUMO structure to be smaller. You will get this entire band distribution, just like you would get in an inorganic system. So it starts resembling an inorganic system, at least for that chain itself, just for that chain. Again, there is a problem of figuring out how to go from one chain to another, or how to get that conduction. But at least in the polymer chain itself, you're able to get very reasonable mobility numbers. I mean, if you look at just across the chain numbers that people have reported in the literature, they're actually very close to what you would get in silicon and germanium and so on. So the orders of magnitudes are there. It's just that going from one polyacetyl molecule to another can be a challenge. So yeah, so this is what I'm talking about. Like pi-pi conjugation is represented like this in literature. I mean, that's of course very well known. I'm showing polypyrrole here particularly because we actually use polypyrrole in some of our flexible piezoresistive materials. So so that's why I'm representing it here. So this is the problem I was talking about, right? I mean, for example, if you have these polypyrrole chains, right? I mean, electrons are very easy, or electrons are able to go from one part of the chain to another because of that pi-pi conjugation, because of that density of state being available across that molecule, but they're not able to go from one molecule to another, right? So if you have a polypyrrole thin film, for example, which will have a lot of molecules in it of polymer chains, that entire thin film from one point to another will not be able to conduct very nicely because of the fact that these chains are separate, right? Now, one of the ways electrons can actually go through this is what's called hopping transport, right? That's one of the things in organic electronics that we see. It's this phenomena basically lets electrons jump from one molecule to another. This is basically just a quantum tunneling phenomena showcasing itself as a electron conduction phenomena. But what ends up happening is that you have a potential barrier here, right? And given a potential barrier, there is always a probability of electrons jumping across it, which basically depends on the distance of the jump and the potential barrier height and some other things. So based on that, you can get a specific probability of this hopping transport. And but one of the problems is, because those probabilities are typically very low in a thin film, you will end up getting very low amounts of conduction, right? So the amount of the amount of electrons that are actually able to hop from one chain to another and then to another and then to another from point A to point B keeps reducing depending on the number of hops you have to do, which means if your molecular weight of the material is not very high, you will not be able to get a lot of conduction through it. But it still is promising. I mean, in thin film form, you do get organic systems to conduct. So like I said, the underlying principle of hopping transport is the quantum mechanical phenomena known as tunneling. And because of the low tunneling probabilities, the charge conduction because of hopping transport is much lower compared to the band transport that we see inside the polymer chain and also in inorganic lattices. Now, because of that, what happens is the average velocity that you will calculate for the entire free charge carriers that are available inside the thin film, that will actually also get lowered. And because that is getting lowered, you will basically get a lower mobility associated with these systems, because mobility is the proportionality constant between the average velocity and the electric field applied. So in general, electrons can be accelerated to very high speeds, but because of the fact that they are scattering at these these junctions, or you could say at these barriers, they are actually their average velocity is reducing, and you will get lower mobilities of the order of something like, if you're getting single crystal silicon mobilities of 1300. In organics, you will get mobilities of around 1. So it's 1000x difference because of this problem. There's another problem in working with electronics in organics, which is the electron hole stability. They're typically in organics, the way the structure works and the screening of charges works, as opposed to inorganic lattices, you actually get a much higher stability in electron hole structures. And because of that, like for example, in inorganic lattices, you will have the bonding between these two is of the order of tens of millielectron volts, whereas in polymer materials, you will have the electron hole bonding of the order of 0.1 eV, or even more than that, like 1 eV and so on. Because of that, they don't separate from each other. And if they don't separate from each other, they conduct simultaneously, that's net zero current, right? I mean, there is no current flowing. So unless you have them separately flowing in a molecule, you will not get conduction or current that we are basically looking for. Although, fun fact about this electron hole stability is that we owe the entire planet owes its life to this electron hole stability, because electron hole stability in chlorophyll is one of the reasons why it's able to generate the chemical reactions that are needed to get from CO2 to glucose. So as you all know, in photosynthesis, you have this ray of light coming in. The first thing it does is create a electron hole pair. I mean, it excites an electron, creates an electron hole pair, the sun ray. Now, once that electron hole pair is created, it has to travel through chlorophyll. I mean, if you actually look at the chlorophyll structure, it has pi-pi bonding, pi-pi conjugation. So it can actually travel to a specific place, and then the chemical reaction takes place, which is the basis of all life on the planet. So we are very happy that electron hole stability is there. But if you're trying to get it to conduct electricity in the conventional way, that's not a very good thing to have. So, like I said, in organic systems, you have binding energies of the order of tens of milli-electron volts. But if you look at these organic systems, you will have much higher electron hole bonding, and they will basically, that again impedes the amount of free charge carriers that are there available for conduction. So the final thing that happens in electron conduction in organic materials is what's called polaron transport. What ends up happening is that if you have an free electron or free hole or some charge carrier going from one place to another, it basically displaces all the the charges that are there, like the stationary charges, which includes carbon nuclei, hydrogen nuclei, and all the other, and it tries to attract them. For example, if an electron is moving and there is a carbon nucleus very close to it, it basically starts attracting it, and it causes it to vibrate because of that attraction. And as it goes along, that vibration is basically follows I mean, the electron is basically, wherever electron goes, that vibration basically follows it, and that reduces the amount of energy that is available with the electron, right? So that's an energy dissipation mechanism that is specific to organic compounds. In inorganic compounds also, obviously, polaron transport happens. I mean, the electron will obviously attract another nucleus, but silicon nucleus or any other nucleus are typically very tightly bounded in a lattice, and they are very heavy. So the amount of energy dissipation that happens there is not that much. Whereas in carbon lattices, that happens more. So it's more pronounced in polaron transport is more pronounced in organic materials. And because of this polaron transport, the net effect that happens is you get a higher effective mass of the electron. The electron behaves as if it's slightly heavier than it otherwise is. And because of that higher effective mass, again, you get a lower sort of mobility associated with the electron movement in the organic system. Right. So we basically call this the electron that is going, instead of calling it an electron, we call it as a polaron, and we associate a specific mass with that polaron, and which is slightly heavier than electron mass. And because of that effective mass being higher, we get slightly lower mobilities. Now, now that we know how conduction works in organics, we will basically go back to piezoresistive sensing, right? How do we get, because we started with looking at skin, and we wanted to sort of mimic skin behavior. So in our lab, what we started looking at is we basically looked at that statement that I made, that we needed to be flexible, stretchable, thin film based, and low cost. That is the thing that we sort of started targeting. And we realized that piezoresistive thin films can be the answer for this, the need to have problem. Piezoresistive thin films can give you the answer. And one of the ways in which we can make these piezoresistive thin films is if we take conductive organic particles and embed them in a matrix, right? So now this conductive, if you look at organic particles, like I said, they are extremely conductive within the molecule itself and have some kind of a mechanism to generate some current across the molecules. So we took these we take these particles, typically called filler particles, and embed them in a matrix to create a conductive, either a thin film or a conductive solid. Now when this matrix is pressed, the particles come close together and resistivity changes, right? So for example, you have this kind of a system where, let's say, you have an electrode here and electrode here, and all of these black particles are conducting, right? For example, because of that, across these two electrodes, you will get some conduction numbers. Now, if, for example, you press it, what happens is that the matrix gets pressed, but the number of filler particles, their diameter does not change, or their conductivity. Nothing changes for the filler particles. All that happens is that they come close together, and because they're close together, now the probability of tunneling is higher. You get more hopping transport, you get more conduction, and because you get more conduction, you can basically see that, like, there's a rise of conduction when we press it. So we use this, but obviously, there is a lot of modeling that needs to be done for this. One of the theories that you have to apply for this is called percolation theory, which is actually a very interesting theory in itself. But what it basically says is that the conduction in a composite or a thin film basically depends on its volume fraction, but it abruptly changes at a specific volume fraction, right? When these particles are close enough just to create a conductive path, like just close enough to create a very high conductive path across the structure and not depend on hopping transport that much. At that time, you get a giant jump in conduction, and then after that, even if the volume fraction is increased, you don't get a proportional jump in conduction because already conductive paths have been made at this point. So this phenomena is basically called this limit at which this behavior is happening is called the percolation limit for that specific filler particle in that specific matrix, right? And if you play around with this, that is where you get a very high amount of sensitivity, right? Because now, if this volume fraction is depending on the amount of pressure that you're applying, right? And the conduction is depending on the volume fraction. So you can get a very highly sensitive material if you know exactly where your percolation limit is for your piezoresistive or for your filler particles and for your entire system. So that is one of the things that you need to model if you're trying to make a piezoresistive thin film or a piezoresistive composite material. The threshold is called the percolation limit, and before this, there's almost no conductivity, and after this, very little change in conductivity for applied, the increase in volume fraction that we get. Now, once we have all of this in place, it's time to do some experiments. One of the things that we do, I mean, in my lab, is to create polypyrrole structures, and one of the interesting things about it is that you can actually create these structures almost anywhere you want, right? I mean, we do it using what's called in situ chemical oxidative polymerization process, in which, for example, you can take a polypyrrole, you can take the pyrrole monomer solution and sort of, let's say, take a cotton pad, dip it in a pyrrole solution, and from there you basically, as soon as you expose it to FeCl3, for example, FeCl3 oxidizes the pyrrole and gives it the sites to create polymerization. And once that polymerization is complete, you will get basically that black polypyrrole structure. One of the nice things about this, I mean, if you're into chemistry, one of the nice things about this reaction is that it's a color change reaction. I mean, I love color change reactions in chemistry because it at least tells me when it's over. So this is that classic color change reaction that goes from a white cotton pad to a black one that is now also conductive, right? So you get conductive fiber, conductive textile. You can, it's very low cost and facile. I mean, you don't have to be in a clean room or anything. You just, you have to procure pyrrole from somewhere, which is a bit of a challenge, but it's okay. But apart from that, it's actually pretty reasonable to do. So again, why is polypyrrole conductive? Now we know why, because it has that clear double bond, single bond, double bond, single bond conjugation that is going across the entire chain, and that is helping it conduct at least across the chain, and then from there you get your hopping. Now, because this cotton pad is full of this pyrrole structure, if I'm going to press this, I mean, it's already conductive. It's not very highly conductive. It's not like metallic conduction, but it's some conduction that you can still measure. Now, if you squeeze that cotton pad and bring all of those pyrrole molecules together, you will see a clear change in conduction, meaning that your resistance or conductivity is now dependent on the pressure, right? So you will get piezoresistive behavior. Right. Now, if you want to know the process, of course, you can follow this paper. This was 2 years ago in FLEPS. But, all we would do in this case is basically take a pyrrole solution and dip the cotton fabric in it, and then put it in the FeCl3 solution for 1 hour at 60 degrees centigrade, at room temperature, and then you get this, and then we just wash it with distilled water to get rid of the excess FeCl3 and unreacted pyrrole. That's all you need to do, and you get the structure. Of course, I mean, if you're a material scientist, you want to analyze this. This is how it looks. I mean, you can see actually these flower structures that are growing on top of one specific, fiber of cotton. So all of those structures are basically pyrrole structures that are growing, polypyrrole structures that are growing there. And like I said, once you do this polypyrrole coated cotton can actually be used. You just need to put electrodes back and forth, right? And connect them to a system that is measuring resistance. And then from there, you can actually get this kind of behavior, right? This is your piezoresistive. This is flexible piezoresistive pressure sensing system. Now, what do you want to do with this? I'll tell you about the applications, but many things that you can do with this. I mean, once you are able to create this system, the applications are limitless. E-skin is only one of them. I'll show you some other applications that we have been dabbling with. But this is the basic thing that we observe. I mean, right? So you have change in resistance with force, which can, I mean, also be represented in the form of change in conductance, but that's what you're trying to get. Now, once you get this structure in place, you still need to sort of be able to read it. I mean, there needs to be some kind of an output that needs to be generated. I typically call this a sensor system instead of a sensor. So what we made is a sensor. This is just what's called a transducer. I mean, it's just transducing pressure information into conductance information or resistance information. But from there, you still need a readout circuitry that will convert it into electrical voltage, right? Ideally speaking. So and then some digitization circuitry that will send that information to a controller. Typically, we'll use a very simple readout circuit, maybe let's say a potential divider circuit. So you will put your resistance here, like the variable resistance here, which is the sensor resistance. You'll have a fixed resistance here and a fixed voltage, and that will basically give you a V out that is dependent on the R2 value or the sense resistance value. Also, you can do something like a Wheatstone bridge that will be slightly more sensitive to what is obtained from a potential divider. But at the end of the day, you get a voltage output. That voltage output can be read using a microcontroller, and you can get a feedback from there. Now, one of the problems is when you're doing these kinds of systems is the what I call the calibration trap, right? Um, because you want to calibrate a sensor, and whenever we are calibrating a sensor, what we are basically trying to do is we are trying to figure out what its characteristic looks like, right? That's what we are trying to do, right? Now, if you look at this equation, for example, one of the problems with this equation is it's not linear with respect to R2, right? Uh, People try to make it linear. One of the easiest ways of making it linear is make R1 very large compared to R2, right? So then R1 plus R2 becomes R1 approximately, and the whole equation becomes R2 upon R1, which is linear in R2. I'll give you that. But one of the problems is because you just made R1 very large compared to R2, R2 upon R1 is now very small, right? So your output is going to be very, very tiny, right? So whichever way you look around, look, there is always a trade-off in engineering, but typically people try to make these systems as linear as possible, right? So for a given pressure, so you're going from pressure that is applied to the skin to the output voltage, and all the way from pressure to the output voltage you expect a linear output. And why you expect a linear output is because of the calibration trap, right? Why is that? Because let's say your output voltage looks like this and this measured quantity is here. In this case, measured quantity is the pressure. That is the independent variable. Output voltage is what you are getting out of the sensor system. Now, why do you want it to be a straight line? Because any other kind of system, I mean, so the straight line equation, that y equal to mx plus c equation has the least amount of parameters that are possible for a two variable system, right? I mean, if you have any other kind of uh, response, you will basically end up having more parameters to deal with in the general case, right? And we don't want those parameters to exist. We want the parameters associated with the sensor to be as low as possible, because sensor characteristics basically ends up, I mean, when you do sensor calibration, it basically means that you're trying to determine the value of those parameters, right? So you don't want them to be too many, right? Two is already very complicated or very difficult to deal with. So for example, if you have this, I mean, obviously from the output voltage, eventually you want the measured quantity out, right? Output voltage is being measured by your processor, for example, it's reading the output voltage. And from that output voltage, it wants to know what is the pressure applied, right? So that is the measured quantity. Now you can do it using this equation. It has two variables or two parameters, slope and c. If you're able to figure out what they are, what their values are, you're good. For any sensor output or output voltage, you will be able to know what your pressure is. Now the problem is those values are actually pretty difficult to determine, because you need very specific known weights, for example, in this case, in case of pressure, to be able to determine what those inputs are. So you need to have a known stimulant on the pressure sensor to be able to figure out what that curve is going to look like. Typically, those weights that are actually very precise and also very low values are actually really expensive as well. So that is one of the problems that we face in trying to calibrate these systems. The other problem is, and this is actually a really big one, the values of slope and c, these two, change with time, right? So let's say you calibrated your skin today, put it on a robot and sent it out, right? Now, 1 month later, if these values are fluctuating, right, the sensor characteristics parameters are fluctuating, it'll sense something as, I mean, it'll basically start sensing 1 kilogram force as 100-gram force, for example, right? It'll be off by a lot. And one of the problems is, if you remember the first few slides, we were going from the real world to the digital world using sensors. One of the problems is processors are kind of blind apart from sensors. I mean, sensors are the only thing they have to see the world. So if sensor calibration is off, there is no way for the processor to know that. All it gets is voltage, and it uses a equation in its system to figure out what the pressure is, right? So that is actually a big problem. So I mean, again, strategies are there to figure out. I mean, in literature, etc., people have done many things. One of the things is, if you can know the drift in advance, right, you can program that in your processor, saying that today the value of slope NC is so much. 1 month later, take that value instead of this value, or have in one sense have slope NC as a function of time in your processor itself. Like, that is one of the ways in which people try to solve this problem. But the other way is, you call back your product and recalibrate it. People do that as well. I mean, in some products, you have to recalibrate it, like the smoke detectors, etc. People say, in 6 months and all, you have to recalibrate them, and so on. So that is one of the ways in which people recalibrate as well. So all of those things are possible, but they are again impediments to the. I mean, they still constitute a problem that needs to be solved as a system designer. Now, finally, like I said, nonlinear systems will look like this, slightly more complicated, more number of parameters, and more number of parameters requires more calibration, and more parameters means that they'll be drifting more, and so on and so forth. So all of those things create problems. In this world, because it's 2025, people are trying to figure out whether we can use AI algorithms to predict changes in sensor parameters and drift in parameters and so on, so that we can predict how they're going to be behaving, and we don't have to calibrate them so often. So that is one of the ways in which people are doing this. Now that we have talked about this, we want to talk also about like the modeling, because we are basically looking at this kind of a system. And when we look at our piezoresistive thin film that we are using and how to calibrate it, typically these are the parameters that you would otherwise have. I mean, in a very large or very general system, where, for example, the sigma is the applied pressure, you have the nominal diameter of the filler particles, the filler volume fraction, the potential barrier height, the original strain, and some constants related to hysteresis and so on. So all of these things are there that are used to determine what the function or how your resistance is going to change when you apply a specific pressure. Now, for a given thin film, thankfully, a lot of them are constant, right? So what ends up happening is we worry about basically the applied pressure and the filler volume fraction. These are the two things that we have to worry about to actually get what the function is going to be. This is from a theoretical point of view. From a practical point of view, one of the things that you can do is, if you have this kind of like a output where you have pressure on one side and output voltage on the other side, and you have basically these fixed resistance values that you're using in your potential divider system, you can basically fit a specific curve and try to fit a curve that is giving you a sense of how the system is behaving. So with multiple attempts, I mean, if you read this paper, with multiple attempts, we basically figured out that this is one of the systems, one of the ways in which we can model our sensor. I mean, the simplest ways in which we can model our sensor is just using a 2-parameter system that looks like this. Resistance is equal to A upon W to the power B, where W is the applied pressure or weight, and R is the resistance that we are getting, right? With A and B being the sensor constants, right? So we have started using this equation in various papers and publications, and we have tried to figure out what the values of what determines the values of A and B and how to control them, so that we can get to the sensitivity of the human skin that we are trying to design for. So at the moment, this is a purely fitting curve based on observation. Theoretical investigations are ongoing because we want to connect them eventually so that we know where this is coming from. But at the moment, this works reasonably well. You can fit it to all of these curves and get different values of A and B. And so if you basically plot this resistance versus pressure, like I said, you can fit these values, those parameter values, and obtain the values of A and B. One of the things that we did is, apart from looking at sensitivity and everything else, we also look at reliability of these systems, right? We try to figure out how reliable they are going to be, because again, that's one of the reasons why, for example, uh, silicon electronics is so successful, right? Because it's extremely reliable over time, right? So one of the experiments that we did is, once we have this sensor system, can we keep testing it for, let's say, 6 months, 7 months time frame? I think we did it for 7 months, and every 15 days, what we used to do is basically take the sensor, test it, do the whole roster of test, and then store it, and then after 15 days, repeat the whole process. We did it for all of 7 months, and what we realized is basically, uh, as any material system, this sensor or this system starts off behaving a little erratically, but eventually settles down to a specific value of parameters, right? I mean, so there is a very classic, this settling that you can actually see in these systems. So if you look at, for example, B as a parameter, because it's an exponential one, after, let's say, 150 days or so, you can actually see it a little more settled compared to the erratic behavior that you see in days before. So that is, again, like I was saying, with time, you need to know how your sensors are behaving so that you can kind of compensate for that if you're making these sensors. So this is one of the experiments that we did for that. Right. So now some quick applications on what basically you can do with these things. So for these applications, we, instead of using polypyrrole based cotton, textiles that I showed, we use, commercially available piezoresistive thin films like Velostat and so on, just to make our life easy and fabricate these structures. Because if you're doing applications, we typically focus on the application side of it and the data analysis and control side of it. For example, one of the applications that we did is basically to detect incorrect exercise techniques, right? I mean, this is, again, one of my master students is into bodybuilding, so he was like, can we create a suit that will tell him whether he's doing a specific exercise correctly or incorrectly, right? So what we ended up doing is, uh, we zeroed in on a specific exercise, and we figured out that in that exercise, for example, it's called deadlift, by the way. If you do deadlift incorrectly, like this is a bad repetition, you will basically see that it's an arching, he's arching his back, right? That's what you're not supposed to do when you're doing deadlift. You want to keep it straight. And because this is the difference between a good and bad rep, what we did is we looked at the muscle systems that are going to be involved in that, and then we basically put a pressure sensor system there, right? A flexible piezoresistive system there. And we try to monitor what those pressures are for good and bad repetitions, right? So for good repetitions, you'll get an output that looks like this out of these 5 sensor pixels. For bad repetition, you'll get something like this. Now, you can always do all kinds of analysis techniques to figure this out, whether it's good or bad. But what we ended up doing is a simple thresholding technique. I mean, we didn't employ something fancy like machine learning or something, which everybody is doing these days. We thought we'll just do it with a thresholding and a weighted average technique. So we do a thresholding and then a weighted average of this input, and if that final thing is above or below a particular threshold, we say that that repetition was either a good repetition or a bad repetition. So we did it with 3 subjects, that are kind of similar in height and weight. because when they're wearing that suit, the pixels have to line up with the right muscle groups that we are trying to work with. But when they do that, you'll basically see that the blue ones here are basically showing good reps, and the red ones are showing bad reps. So you can clearly see that at a specific threshold, everything above this is basically bad rep, apart from a few misclassifications. We are getting a reasonable classification for all the three subjects. This was in Census Conference 2022. And then we started working with, let's say, can we make a chair that will detect falling, for example, right? So let's say you have these pressure sensor pixels now positioned on the chair like this, and when somebody sits, they all basically give a particular response. Now if somebody is leaning, these two pressure pixels are not activated at the back, and something like that. And then for example, if you slide out of it, all of them get deactivated. Now whether you can write an algorithm to know if somebody is falling from the chair or not, or whether they're sitting correctly or not, this is again one of the ongoing things that we are doing right now, trying to figure out that algorithm to see whether it works. Then we, as you can see, we are getting bolder and bolder in the applications that we are doing. So we basically we made it even bigger, and then we said, okay, can we put it all across a bed? This was in census letters last year, and see whether we can detect whether somebody is falling from the bed or not, or where they're sleeping, or so on, right? So for example, we have this system where if you're sleeping in the middle, you will have these pressure points being activated, and as he goes on that side, you'll have these being activated. So he's just based on that pressure output, you can know where that person is, and whether he's, for example, about to fall or not, can actually be determined from that as well. And again, this is like a 6 feet by 3 feet structure. We went one step further and created a structure that is now 5 meters in length. All of this is a single pressure pixel. I mean, the entire horizontal line is 5 meters in length and something like 15 millimeters in width. That is the entire pressure pixel one. And there is another pressure pixel that is going in parallel with it. So there are two pressure pixels. So there's two lines on which you can drive this. By the way, when we were doing this experiment, I swear I thought the moment I drive one car over this, the thin film will be dead. Because we use copper electrodes, they will be dead. The velostat thin film will be dead, and everything will just ground to mush. As it turns out, that's not the case. I mean, it actually gives you reasonable response. So again, you can find this in census letters, and you read about it. But the theory is that if you have this on your road, you can actually do a lot of things with it, because one of the things that you can do is, because it's the distance between these two pixels is known to you, right? If somebody is driving over it, you can know at what speed they drove just by figuring out the speed, the difference between the two changes in pressure that you get for those two sensors, right? That is the one thing that you can do very quickly. That is the speed. But you can actually also do other things. For example, you can do weight of the vehicle just by calibrating the sensitivity of it, right? I mean, if your system is sensitive enough, or in this case, not very sensitive, you can actually, just by how much the dip is, you can figure out what the weight of that vehicle is, right? So now you know the speed and the weight of the vehicle. Now you can also figure out if you basically have, because typically vehicles will have two axles, most vehicles. So if you have those two axles coming in, you can, because they'll activate the first sensor, second sensor, and then the second axle will activate the first sensor and the second sensor. The difference between the activations of two for the same sensor for different axles will actually give you the length of the vehicle, or what is the difference between the two axles, right? Because now you know the speed of the vehicle, you can always determine that. And the width of this dip will actually give you information on tire pressure, like how flat the tire of the vehicle is. So all of that information can be obtained just by putting two pressure sensor pixel lines across the road, right? Extremely low cost, extremely flexible, portable system. So do read about this. And we are trying to now expand it with whether we can. One of my students is trying to do this experiment with, let's say you have two parallel ones, and if you have one that is tilted, like at a specific theta angle, can we also find on which lane the vehicle is? Because now you have information about the the difference in the x-axis as well. So all of those things we are trying to figure out and trying to make the system more interesting as we go along. But this is one of the applications that we have. Now, apart from this, I mean, and this is a classic application. I mean, a lot of people demonstrate this where you can put this in your shoe and walk around and do all kinds of things. But so many papers are basically on figuring out, for example, the gate, pressure distribution, and number of steps using this. What we did is we did something different. We said we'll wear this and we will try to determine the properties of the surface instead of the property of the individual, right? So that you can do. Again, this is last year in census letters. You can read about it. It's overlapping right now. I mean, but the back image, which is there you can read it in the paper. The back image basically shows you a person trying to walk on two different kinds of surfaces, like a sandy surface and a tough surface. And when they're walking, you can actually train an algorithm to figure out whether at what kind of surface that person is walking on, right? And get information about that thing. I mean, we are trying to see whether we can sell this to sports complexes where they want to know the softness of the grass, etc., across the pitch and so on. So that's actually a very interesting application that we're excited about. Now, finally, like I said, I told you we'll talk about the dual sensing problem as well. So one of the ways in which you can get dual sensing is this kind of a structure. I mean, we're doing crossbar architecture for a lot of these applications, and that's very well studied and reported as well for all kinds of pressure sensitive thin films. But if you modify the crossbar architecture like this, where let's say you have a common terminal in the middle, and you apply these two different excitation voltages from, let's say, the top and the bottom, you can actually get a pressure sensor and the temperature sensor both in the same footprint, right? So there's a poster outside depicting this, and this paper is going to be in the proceedings, so you can read about the details there. But what we are trying to do here is we have a pressure sensor here and a temperature sensor here, sort of clubbed together in a thin film form, right? So on that same vertical footprint, you can actually let's say put a weight that is also hot. So we basically heat this weight on a hot plate and then put it on the system so that it does both pressure application and heat application at the same time on the same pixel. And in that paper, we have basically shown that it does, our system is able to differentiate between just pressure, just temperature, and both very nicely. Of course, this is very sparsely distributed right now. This is one of the first demonstrations like this. So we want to make it tighter and tighter in terms of spatial resolution so that we get it to the levels that humans are. But this is one of the dual sensor techniques that we are demonstrating this year. Apart from that, I mean, I actually have a live demo as well. I just wanted to show you guys how it works. It's actually a very simple system. That's why I thought I'll demo it here. So this is how you can make it, like I said, do it yourself pressure sensor kit, flexible pressure sensor kit. So if you have this, let's say you take a paper substrate, right? You put a copper tape on it and then let's say solder it to make one terminal. You do the same thing on the other page, and you take this commercially available velostat, pressure sensitive mat, and all you need to do is this. You put this horizontally, this vertically, for example, and create this structure, right? Now, once you create this structure, as you can, I mean, as we've discussed, the way electrons are going to go is, let's say, from this terminal on this electrode through the pressure sensitive thin film on the other side, right? So you can create these systems, and let me see if this works, and have let's say an Arduino. So if, for example, if I press this, it goes down, and if it will come back to like 1000. If I keep pressing it, it'll keep going down, and then so on. So it's a very simple system that you can create. You can basically bend it, and it'll basically sense that as well. So it senses both bending as well as pressure. And uh, you know I've already shown you six applications of this, and at six different publications that we have with us. That's basically, I think, if I count, like one PhD and three master students worth of work that we have done just with this system. I mean, it's very low cost to get. And the reason I'm showing it here is because I want you guys to experiment with it and, play around with it and do whatever. And if you want, you can actually take this with you uh, and play around with it. And uh, who wants this system? Anybody wants this system? Free giveaway. Okay. Because there are multiple suitors for it, I will have a quiz. Okay. So answer the question and get that system. Ready? It's based on what we just learned. Okay. What is the name of the theory used to model the conductive behavior in composite materials? Okay. If nobody else, yeah. Okay, I'll give you. It's percolation theory. Yeah. You can take it. Don't despair. I have one more. One more system up for giveaway, and one more question for it. I think it's an easier one. Describe one way in which organic conduction is different from inorganic conduction. Inorganic lattices. For this. No? No one? Sorry? It's pi-pi bonding, but yeah, I mean, I'll give you that. Thank you, Professor. Thanks. All right. That's my team, by the way. Very happy bunch of people working on various aspects of experiments that we just saw. Thank you all for listening.